Hi, in this topic, we're going to talk about stress and strain. And in this first part, we will concentrate on what is called the state stress of a point in a body. So the important thing here is that we will have as an objective is to answer one question. This question is going to be a very simple question, and that is if the part that we're studying is if that part will break. Last time in my last video, I commented that one of the important things that we are going to be evaluating here is that if the part that we're designing or the part that we are going to be evaluating will fail or not under certain conditions. And also, I mentioned that a failure of a part can be considered as if the part breaks, kind of that the forces applied to the part are to such magnitude that internally the part will break, we will kind of exceed the stress, the stress limits, and then the part will kind of just fail by breaking apart. Or if the part will deform to such extent that their functioning or the operation of the part is no longer possible. This is where I want to mention about our main objective here, because it is important to find ways or find tools to assess if the part will endure to do the job that we want it to do. So the objective is pretty simple. Just ask a question, will it break? And in this course, we're going to try to provide all these tools necessary to answer this question under our designs in a more analytical way. This is the first part. So how to introduce this topic? How to introduce the topic of stress, or what's the name? State of stress. In this case, state of stress is what is going to allow me to determine if the part will how are the external forces acting or causing sorry, the audio was muted. What the external forces are causing inside of the part. So as an introduction, we have to understand something. Let me finish this. State of stress. If I write something, by the way, if I write something incorrectly, please excuse me about that. It's totally new for me trying to write while talking and trying to pay attention that I'm kind of making a nice font that you can understand later. We'll try to do my best here. So we have to understand that when we're talking about the materials we're going to be dealing with, they're made out of atoms and molecules. And in our specific case, solid materials, we talk about crystals, granules, or association of different materials into one. So we're going to understand, or we're going to try to understand how the material behaves under the influence of loads, external loads. And that's what is called the rheological behavior of the part. Let me write it down here. It's called rheological behavior. Yeah. And basically that says that, okay, how it's going to dictate how the material is going to deform under the action of forces. This is what we're looking for. We're going to see, for example, in a ductile material, if under the action of forces, the deformation is going to be such that it's going to exceed this proportional linear, or this linear proportionality between the stress and strain, and it's going to reach the maximum admissible, and then it's going to break later, or it's going to be permanently deformed, or where it's going to be located, that deformation. So this is a very difficult thing to quantify, the rheological behavior. This is not an exact science, and because it's a complex phenomena. And what is done basically is to idealize by means of physical kind of mathematical models, we try to reproduce kind of, or to understand the most important features observed in these experiments or tests. And then from it, we try to kind of extract the better, in the better possible way, a form to describe that phenomena. But it's kind of, it's not a fully theoretical, let's say, derivation of what's happening there, but is more kind of an approximation of what is happening in reality. And that is managed through something called the phenomenological approach. So we just observe the phenomenon and try to explain it, or give it an explanation. For this, one of the important considerations that we're going to be making here, and it is done in many of the textbooks, is that the material doesn't have any discontinuity. It means that the material is continuous in the whole structure of what we're studying there. So if the material, we consider that the material is always continuous, it means that whatever functions we use to describe forces or displacements and deformations are also continuous functions. We consider also the material is a kind of in a mass point, kind of, we're going to consider that the material of the different points which the part is consisted of, it has the same properties along the whole, let's say, part. And basically, we arrive to the conclusion, or not the conclusion, but to the major premise is that we are going to be using something called continuum mechanics, because we're going to assume that the part, even though it's not the way, is a continuous media. Let's say that it is said also that when dealing with the subjects that study or deal with continuum mechanics or studying material mechanics, is that they have two big divisions, and one of them is mechanics of materials, and the other one is called or related to studying the deformation of that material. And what we're going to do here is we're going to do many assumptions in the way we're going to approach these problems. For sure, there are more complex ways to study this topic, but our level, I believe, is a very good starting point to propose these kind of solutions that are very well accepted in the mechanics of material world. So let's continue here. One important thing to define is something that you already know, is that any action consider or acting on the body, everything that causes deformation, everything that is acting on the body is going to have a consequence. So this consequence is going to be, let me write it here. We have actions on the body, and that's going to produce certain consequences. These consequences might be in the form of deformation. We are going to have responses to those external forces or actions via internal forces. That basically, kind of, I'm redundant here, but internal forces are those we're going to call deformation. Any external force can also cause on the body, you know, if it's a free body, if a free moving body, it can cause acceleration. It can cause, you know, change in mechanical properties in the case we're applying some heat to the part. We write them down here. And many other things. Again, to keep kind of definition, even though I'm repeating this, you have already seen this. I want to get to an agreement that we're going to say that to the body, or we're going to be dealing with, to the body, we're going to be applying or can be applied the different type of forces. So we can have external forces, which can be divided into surface forces, for example, like weight of the non-structural parts. We're going to have inside of external forces could be mass forces, that is the own weight of the part. We can have there, I'm going to keep scrolling down here, rigid body motion. And for sure, or we could have deformation. It is said that the part always deform to a certain extent, but sometimes the deformation is so small that we just neglect it. Formation. And in this part that considers state of stress of a point, our main characteristics or our main topics to discuss is what is the relationship between stress and strain. We will define, you know the definition, the base definition of stress and strain, but we will also define it here to keep it consistent. Great. There is a lot of theory or material that we could be introducing here, but let's put it in this way. This theory or these concepts are already familiar to you. I'm going to focus on those concepts that are totally new for you. For example, the three-dimensional case of a state of stress and strain relationship. We will that's going to be our main focus here, because in the end, we want to find a way to know that external forces applied to the body are going to create internal forces. These internal forces then are going to create stresses, and they're going to create strain that would modify as we mentioned here, they're going to cause certain reactions on the body, like deformation or acceleration, if in the case of rigid body motion. And then according to that, we're going to decide if that part is suitable to do the job that is designed for or not. So this is why we're going to start now, or enter here in what is the stress tensor. Take it to the top of the page. So let's imagine a body. I'm going to try to draw peanut, kind of a peanut-like body here. And this body is going to be subjected to external forces. It doesn't matter now how these forces are applied or what are causing these forces. The important thing to consider here is that the body is under external forces. If I take a look at a point inside of that body, and I try to open the body like I am trying to open that body here, or cutting that point where cutting that point in a way that a plane, the cut plane, passes through the point. I'm going to find some interesting properties here. I'm going to try to draw this again in this area. This shape, this is the cut body. We still have forces applied here and here. I have the body, the point, sorry, in here. And if I take that plane, the cut plane that passes through the point, and I draw it outside of the body just to make it better, it's going to be something like that. First of all, we know that when we separate and we cut the body, we are going to definitely have reaction forces here that are going to pertain to the separation we just did. So we are going to have a kind of a reactive moment and a reactive force that's going to be complementary to the other part of the body. In this case, if I take, that plane that passes through the point, it's going to be something like this. To draw here. So I have the plane here, and to that plane, it's going to be applied a series of forces. If I say that we start using a Cartesian coordinate system here, x, y, and z, I can say that on this plane where the body is, I'm going to have a force applied to it. But this force can be divided into its Cartesian components. I'm going to have a force here. Actually, I'm going to write it delta fx, delta fy, and delta fz. And the reason for that is that it is considered that as the material is homogeneous and continuous, I'm going to consider that I'm working with an average force applied on that area. So not a specific force, but an average force. So in this area element, or delta area element, I'm going to have the following definition. So we know that stress is defined as the limit when this area turns to a very small dimension of the relation between the force and the area. That we could rewrite this saying that the stresses are, or the stress is equal to differential of force divided by the differential of area. There you go. This is in the general way, but if we're talking about the different components, then we can do the differentiation saying that if I consider that the delta fx, or the force in the x direction, is normal to the plane, let me write it here, normal to the plane, and these ones are on the plane, kind of tangential to the plane, I can name these the stresses caused by these three forces. They can be named as such. We can have sigma x, x. I'm going to write it this way. You can find it also in other textbooks as sigma x, but I will try to write it all the time, sigma x, x, because I want to explain later a certain naming convention that we're using. This is going to be equal to the differential of the force x divided by the differential of area. Similarly, this other stress caused by this force y and force z that are on the plane, we're going to call it this tangential vector, or the shear stress is a tangential vector here. I will call it xy, for example. It's going to be equal to the differential of force in y, differential of the area. And finally, we move this a little bit ahead. There you go. Shear stress, the xz is equal to the differential of the force in z direction divided by the differential of area. Then we have something that you already know, but I'm reintroducing here. That is, this is the normal stress. These are shear stresses. Normal because it's pointing normal to the plane. We are studying, and shear because they are tangential to the plane. And when I said that I like to write this normal component, even though I can write it in this way here, I'm going to write it with the two subindices, is because of the naming convention I'm going to explain right now. Before that, I will try to draw this point. So our point here, I can represent it as a cube, as an infinitesimal cube where stresses are applied to. And that's going to allow us to formulate many of the equations of equilibrium and many of the relations we're going to need to calculate magnitudes and parameters on these type of problems or infinitesimal cube. Let's see. I'm going to start by drawing my reference system. Let me use this one, show, or the cube better. I'm going to have a cube, more up. Let me see. Yeah, this one. And to have the infinitesimal cube drawn like this. Let's draw all the phases. So this is going to have 6 phases. So each one of these are the positive phases when I'm looking at them. Trying to, yeah. I will have, let me draw the kind of the hidden lines here. These are going to form the hidden phases. We'll draw at once the Cartesian coordinate system. This is pretty important to define the equilibrium, and whatever we're going to do next needs to be done under a Cartesian coordinate system. This is y, and we have z-axis. Yeah. I want to make it big so it doesn't make a mess. Yeah. On each one of these phases of the cube, I'm going to have a triad of stresses. I'm going to have per each phase 1 normal stress and 2 shear stress. Let's start writing the first one. Let's use blue one. In here, say in this phase here, I'm going to have a normal stress sigma xx. I will have my first tangential or shear stress, and this is going to be xy, or name xy. And here, this is going to be another shear stress. This is going to be tau xz. Then in the y direction, I will have sigma yy, normal stress. I will have tau yx, and here tau yz. I believe I will keep the same color here. In this phase, I will have sigma. No, this is not normal. Draw the normal here. Sigma z, tau zx, and tau cy. So these are the stresses triad located in each one of the positive phases. And I call them positive phases because they are in this quadrant where all the components are positive. If we go to the negative phases, or the hidden phases, you get the idea. We're going to have normal vector, normal stress here. And I will have, of course, I'm going to have here these normal stresses. And also we will have the corresponding tangential stresses. I will have, as an example, I'm not going to write them because it's going to be a mess, but no, these are going to be here. Yeah, this is, for example, it's going to be tau xy, and then this is going to be tau xz. And these were the convention comes important or using these two sub-indices. So for example, if we have just trying to hide this. Just a second. Yeah. So if we have for a pencil here, yeah. This stress here, there is written using two sub-indexes. The first one is going to be, no, battery life. That's not a problem. The first one is going to be the applied phase. So where the stress is applied. And the second one is going to be the pointing axis. Now you say, okay, this is very clear or pretty straightforward with this, what I have done here. Because, I can see right away that, I try to press this. Yeah, maybe it's better this way. Because, these are XX, so what's the difference how to combine these or how to utilize them. But let's study this one. Let's take, for example, tau xy. The first one is going to be the pointing phase, the applied phase, sorry. And you see that tau xy, this is called, let me mark it like this. This is called the X phase, X positive phase. And then, because, it's where the normal stress in X is coming out of or from. Then you have shear stress YZ, and that represents, that's why when I have the first subindex here, this X is representing the applied phase. And that's why you notice that for example, in the Y phase here, your shear stress is the first subindex is Y. Then the second one is the pointing axis. You see that it says that it is pointing in the Y direction. In this case, the tau Y, YX, it is located in the X phase, but it's pointing in the same direction of the Y axis. So this is a nomenclature we're going to use in this case. I hope that's pretty kind of understandable, because what I'm going to do next is to explain what is going to be for us a positive stress and is what's going to be a negative stress. Let's see here. We need to use some sort of convention for this kind of to decide if it's positive or negative. We will use to this purpose what is called the Von-Karman convention. Von-Karman says that a stress is positive if it is located on a positive phase and it is pointing in a positive direction. Let's understand this. Yeah. Positive if the stress is located or represented on a positive phase and is pointing in positive direction. then we're clear that, for example, those stresses represented in the yellow area here in the positive X phase, this one here, all of these stresses are positive because they are located on a positive phase, and each one of those stresses are pointing in the same direction of the positive axis. For example, a normal stress, sigma xx, is located on the positive phase and pointing in the same direction of the positive x-axis. The same happens with the shear stress xy and the shear stress xz. Also, we're going to say that they are going to be positive if the stress is located on a negative phase. Stress is located on a negative and it is pointing in negative direction. Under this convention or under these assumptions, all of the stresses drawn on this cube here are positive. For example, let's take this one, the shear stress xy represented on the negative phase. This stress is pointing downwards, and it says that this stress is positive because it is located on a negative phase and it is pointing on a negative direction. If you see the y in here, this is pointing downwards, and it means that it's pointing in the negative y direction. So this stress here is considered positive. And this is what we call, the Von-Karman convention to define if a stress is positive or is negative. So whatever contrary to this is definitely the stress is going to be negative. We're going to use this convention always. So keep this in mind all the time. Next, I'm going to talk about the kind of equilibrium of these parts. So we're not going to be dealing with a rigid body motion. It means that our parts are static, and the movement these parts are going to have is because of external forces applied to it or external loads applied to it, causing some effects inside of the part. So external forces applied to the part that causes internal forces that in turn, causes deformation or any other phenomena there. And we're going to be interested in that. So our part is going to be static. And if it's static, we can take advantage of the equilibrium conditions, rotation equilibrium and translation equilibrium. And that's kind of what we're going to do next, or I believe that I'm going to cut the video here and I will jump to the other video where I will be explaining what happens with the equilibrium when we propose or we write down the equilibrium conditions for this cube. We're going to get very interesting relationships between the shear stresses, and we're going to get a way to calculate forces in our cube or in our infinitesimal cube by using these equilibrium conditions. So I will talk to you then in the next video. Thanks.